I'm going to start with a little bit of a warning. So you have the slides available online in PDF format. I've prepared a lot of animations for these slides. Unfortunately, GIFs can't be rendered in PDF. In all the slides where you might see a blank figure, there's a link to get to the proper animation. So all the animations that you'll be seeing today, you'll be able to see them at home as well. And there's also the code available that I use to generate these figures in case you're interested. So let's get started. So for the contents of today, we're first going to start with an introduction and intuition to convolutional neural networks. And by the way, the term convolutional neural network is a bit long. It's a lot of syllables. So I'm going to use the term CNN as well interchangeably. So if I say CNN, I'm really talking about convolutional neural networks. So we're going to talk about the mathematical operations involved in CNNs, so understanding what a convolution is, how it fits in the context of a convolutional neural network. And we're then going to talk about the motivations for using CNNs. Why are they so useful? Where do they fit in the deep learning pipeline? And then we're going to look at how a CNN can be thought of as a building block. So the image that we have here, hopefully by the end of this talk, will start making sense to you. So let's start with a bit of an introduction to CNNs. So CNNs, again, convolutional neural networks, are a very specific type of neural network. And they were really designed around dealing with data with a grid-like structure. So what does a grid-like structure mean? It means data that has a temporal aspect, for example, like the signal that we see here, which is an EKG signal. So you might have some kind of device that measures at a certain frequency at a very specific interval. It will take some measurements, and you can read those measurements and interpret them. We can also have a spatial grid structure. So for example, an image, where each pixel in an image will represent some kind of spatial extent. So it might be that the difference in between two pixels is actually translated to some distance in the physical world. But it's very important that we try to exploit the fact that the distance between 2 points on the signals that we're measuring are constant. So CNNs were actually some of the first deep learning models to be shown to generalize to useful tasks. And deep learning has exploded in the past 5 to 10 years, but CNNs have been used for a long time. In fact, in the late 1990s, approximately 10% of all checks that were written in the United States were being automatically processed by a convolutional neural network. So while deep learning is still new, let's say, in the industry, and it's now taking off in terms of popularity, deep learning has actually been used in production for a very long time. The issue was that apart from doing optical character recognition on a task like checks, it was very hard to train deep learning models on other useful tasks. So up until 2012, more or less, that was a huge point for deep learning when we had this model presented called AlexNet. And we're going to talk about AlexNet much later throughout the day. We're going to go in depth into what AlexNet was and what ImageNet was, which is a competition that it won and why it was so important. But it's really around 2012 that people started paying attention to convolutional neural networks a lot more, because that's when they started realizing the potential it had on actual images and on useful tasks, and that the hardware was now up to date and in keeping up with training these models. But again, we're going to go through all of the details of this network later on today. So why do we use convolutional neural networks? The intuition behind it is really to get the network to focus on local features. Or you can think of this as patches in an image. So one kind of mental sketch that you might think of is, say that you have an algorithm that is trying to detect a face. Well, you might try to think of it as something that's looking for nose-like features, eye-like features, ear-like features in a certain combination of ways, such that by combining these features in a specific order, you might then be able to reconstruct a face. This is similar to what Gaetan was presenting with the chair example yesterday. So we don't necessarily know how to abstract a chair, but we might want to look for certain local features that might represent the chair. This is true for a face. This is true for cars. So let's take an example here. Say we are looking for a car. Our network might first focus on a set of features that are quote-unquote wheel-like. And then this gets passed on through and through our network, and we can eventually decide to make a decision based on probabilities whether this is really a car that we're looking at. It can also take the information and say, well, there is something that looks like a mirror, something that looks like a car-like feature. Combining all these different features together, we can then make our prediction more accurately. And again, the whole point behind CNNs was to force the network to focus on local patches and combine them in a smart way.